Good afternoon, everybody. Welcome to our talk. I am Kartikeya, and I have with me my colleague, Ryan. We both are part of the service mesh team here at Intuit. And today, like the title mentions, on-call the easy way with agents, we will be talking about how we are trying to reduce the toil on our on-call engineers by using AI agents. So just to get started with a brief overview of the agenda of the talk, we will be starting out with the technology here at Intuit, followed by the scale at which we operate the service mesh platform. This will be followed by the overview, which includes the challenges that we noticed and the proposed solution that we came up with, which is basically the agent. And just a high-level overview of what an AI agent is and how do we build such agents at Intuit. This will be followed by an architecture of the agent we have and an example of the results produced by it for an example query. Finally, we will go about the benefits and what our future goals with the agent is. So, some of you might already be aware of Intuit, but for those of you who do not know, Intuit is a global financial technology company that is serving over 100 million users across our 4 different products, which is TurboTax, QuickBooks, MailChimp, and Credit Karma. We as a company are big users of open source technology and have a commitment to give back to the open source community wherever we can. So talking about the scale at which we operate our service mesh platform, before we dive deeper into the agent, is so we are spread out across 350 plus Kubernetes clusters. And within those 350 Kubernetes clusters, we have approximately 2,000 rollouts and deployments. And talking about daily metrics, we see a daily transaction of over 16 billion and a peak TPS of 292K. So now that we are aware of the scale at which the service mesh platform is, we can well understand the interesting problems that come along with it. And within that, we want to focus on the debuggability aspect of it. Working with such scale means that you are generating a huge amount of data through all the interconnected services that you have, through logs, metrics, and metrics. So when you face an issue, there might be issues that you are already aware of, for which you have your dashboards and runbooks set up. But what about one of those issues that is new and complex? Or maybe there's a situation where you have new engineers on your team, and it is their initial few shifts of on-call, and we all know what a steep learning curve that is. In cases of an incident, you might spend a lot of time coming up with some complex queries or going through documentation on the fly. In a high-pressure situation like that, it becomes tough to pinpoint the root cause of the problem. So this brings us to the main topic of today, which how do we streamline this process and provide our platform engineers with something more to assist them? So this is the solution that we proposed. Can we build something that can read logs and metrics at high volume? Something that can utilize all this information and analyze them and match it to a probable root cause? Can there be something that can be equipped with predefined tools to quickly resolve those issues? And we believe this is a perfect use case for an AI agent. So what is an agent? A program that can independently observe, analyze, and make decisions to solve a problem. So if we just see a high-level diagram of what an agent does is a user comes up with a particular query. That's when the agent runtime kicks in. And then you have your orchestration layer, which communicates with the LLM or a model of your choice, which does the reasoning and comes up with a plan to solve that problem. And you also provide it with the tools, which can be used to, say, fetch data or perform certain transactions before actually providing a result. Once it has the finalized results, that is returned back to the user as a response. So how do we build these agents here at Intuit? We have a payroll solution called GenOS, which helps us design, build, and deploy any generative AI application or capability at Intuit. And it provides the framework too, like in the diagram that we saw before, access to the different AI models, and the agents and tools registry. Along with this, it also gives us capabilities to do the tracing and debuggability, also solve for the agent memory, be it short-term or long-term, and also do the agent evaluation. So now that we have a basis of what the problem that we are trying to solve, what an AI agent is, and how we develop it at Intuit, I would like to hand over to Ryan to go over a deep dive of the agent that we have.
Thanks, Kartikeya, for providing that overview of what we do at Intuit and also some of our capabilities before we're able to go into this simplified architectural overview. So this is going to be an actual overview of how the agent is deployed, how it's constructed, and kind of its inputs and outputs. And we'll begin with this first block here, which is 3 different forms of input that the agent might be able to accept. And these kind of correspond to a typical on-call duty of like debugging, answering internal customer support questions, or maybe reacting to an alert. So it could be deployed as a chat agent that the on-call engineer can talk to, maybe as a Slack bot that internal customers can work with directly, or it could be just triggered directly from an alert. Since we are a traffic platform, that initial input to this agent usually contains something like a transaction ID or some other unique identifier for something like a failed network call. From there, following along with the typical on-call process, we want to make sure the agent has the correct context and additional debugging information that we want it to have. And this is information that we expect to have for basically every debugging session, and includes a lot of things like logs for the source and destination assets, Wavefront metrics relating to uptime, maybe change logs pertaining to underlying infrastructure, and also the additional user information that's being passed along. And you can think of this like the dashboards or information that you've got open in your 50 or so tabs whenever you're on call, right? Next up, it's going to pass through the actual mesh retrieval augmented generation layer, as well as through to the LLM. And this is a critical component in helping the LLM actually understand the service mesh platform and also your company's specific processes and information. This step is essentially able to just add the additional context to the LLM based on the current input. And we'll go into more detail as to how this works and what kind of information we actually provide to the RAG layer later. The combined user input, added debugging information, and the additional context provided by this layer all get summarized by the LLM, and that's being used to actually select the tools that we've provided to the LLM. And each of these tools is basically just going to be a standard function that's attached with a natural language description of what it does and of each of its parameters, which the LLM compares against its current input. And in our situation, we might provide the LLM with tools corresponding to runbook steps, the ability to make more specific queries corresponding to whatever data it thinks that it needs, and also some sort of actionable tool, like maybe dry run kubectl access or anything else it might need. After tool selection, the model parses its current information, grabs the tool parameters, and then actually runs the tool. And that output of the tool call is going to be returned back to the LLM, and this process repeats until the model is able to stop. So earlier I mentioned that retrieval augmented generation is one of the critical parts of this process because you're general LLM is not going to have access to mesh information or to your company-specific information. And we're going to go into a little bit more detail about how we specifically perform retrieval augmented generation here. So as we mentioned earlier, we need this to be able to provide additional context based on current input. And the first thing that it needs in order to do that is a collection of documents for this layer to pull from. And if you take a look at the slides here on the left, these are kind of excerpts from our own internal documentation and also something like publicly available documentation. These are Envoy response flags that are often pulled into Istio error logs. And some additional things or examples that it might include is internal team documentation, RCA docs, architecture reviews and tech specs, and customer-facing documentation like frequently asked questions or getting started guides. These documents then end up going through an indexing process that results in a vector database, which is going to map from that embedding to chunks of these documents. And when input is passed through to the agent, it's going to first pass through that same embedding model that we use for the documents, and that gets compared to the actual embeddings in the vector database. And the score based on that comparison is what allows it to pick out the correct chunk of information. This process is going to be repeated on the tool outputs that get sent back to the model so that as the debugging process keeps going, it's able to attach additional context based on the tool results. And luckily for us, using the GenOS platform that we have, a lot of these steps are going to be done for us besides the actual collecting of the documents. And this helps us move really quickly when we need to update the knowledge base of the agent. So for agents, another critical step is that tool selection process. And it's possible that this is actually going to be even more important than the tools themselves, because what's even more dangerous than not being able to do this kind of debugging is if you pick the wrong tool and the wrong kind of step is executed. So it's essential that you do as much as you can to make sure that this tool selection process goes well. And in our experience, the most critical step for getting the model to select that correct tool is making sure you have proper descriptions of what your tool does and what those inputs are. And it's important that these descriptions are in a natural language format, since that's what LLMs are going to be trained to understand. But if you think about how you normally write code and maybe how you normally document code, these go against our existing conventions as engineers, right? When you name a function or a parameter, you're going to do that with some sort of intimate understanding of how it's actually going to work, or maybe upstream or downstream usages of that parameter. And if you think about something like writing a function to undo a payment transaction, you might name that function something like reverse transaction or revert record or something like that. But a user, and similarly an LLM, is not going to think of that as a reversing a transaction, right? They're going to call that something like a refund. So you have to make sure that your steps, your actions, are going to match the natural common language format. And additionally, you just need to make sure that the language of the tool descriptions also matches what's in the documentation that you provide, since the docs are going to be the context that the LLM uses to select these tools. So if we zoom out just for a second and we look at these other two bullet points, the co-located versus remote tools and the model context protocol, what I mean by co-located is just a tool that's running in the same application as the agent. And a remote tool is just going to be running in a separate application. And how that interacts with the model context protocol and why this is generally important is because the standard of the protocol is what allows the agents to talk to tools that you define, and also that tools that other teams and maybe other organizations are defining. And when you're able to create something like a tool registry or an agent registry, that allows you to really extend the power of your own agent and allow other people to use your tools as well. So we mentioned that this is like a mesh-specific debugging agent. We're currently looking at other teams trying to build like a full-on incident response agent that can call our tool and any other platform-specific tools. So now that we've talked about how the model might end up selecting tools to run, I'm going to walk us through an example of how we actually come up with tools. In our use case, we typically look at our existing runbooks and we try and translate them into a series of tools for the agent to select from. So you can see on the screen here, this is an actual excerpt from our runbook for UC errors in Istio. So first of all, we'll note that this has to be a document that's provided in the documentation that's available to the RAG layer. It's likely that the runbook title here, the UC, and also the destination services causing connection termination, that's going to be picked up by the LLM and allows it to pick up the rest of the steps here from the documentation. If we continue reading through this runbook, you'll see that there are a couple of validation steps here to see what the root cause is. And these are additional queries that we would typically be running manually while we're executing this runbook. And if we want the agent to be able to do those things, you're going to have to write tools to query your logging or monitoring tools to, for example, pick up the Kubernetes namespace or the Kubernetes cluster here and all of these other steps. Next, you can see that there we have some mitigation steps that are written here. And in this particular case, it's just contacting a destination service owner. And in order to do this, the agent, once again, has to have a tool written to actually do that action. And in this case, it might be some sort of Slack integration or maybe a Pagerduty integration. And if we just keep moving on to other possible root causes, you see another tooling that executes some sort of data query. And finally, the last mitigation step is an actual action where it says, you may want to bump up the memory. And that might correspond to a kubectl tool, or maybe some sort of PR generation to edit the HPA or the rollout in order to actually perform that action. So now let's take a look at what an example call to the agent actually looks like. And this is in the context of some sort of on-call engineer actually making a call to get some help debugging this specific transaction ID. And in this example, you can see the user, which is this red square at the very top, is providing just one single piece of information. And that's the transaction ID of the failed call that they're debugging. And the agent is able to parse the user input for that TXID. It grabs the initial debugging context and executes some of the runbook steps that we saw previously. And you can see that it's able to pick up the cluster and the namespace like I mentioned before. After that, it's able to analyze the logs, determine that some sort of upstream service is unhealthy, and then offers a couple of next steps in the debugging process. And you can see just how much time and effort this is going to save for an on-call engineer who no longer has to perform all of these debugging steps manually, and also how extensible this capability is. So this is just a couple steps in a very specific error path. And once you have dozens of tools for dozens of different runbooks, right, the agent is able to compose a series of steps to maybe solve an issue that you haven't even seen before. So that's a deeper dive into how the agent works and some of the development process behind it. And I'll now hand it back to Kartikeya.
Thank you, Ryan. So moving on to what are the benefits that we have seen while we've been using this particular agent. So we have something that summarizes information across the different dashboards, logs, metrics, and runbooks that we have to provide us with next steps. It is able to handle complex systems that otherwise have a steep learning curve. It is able to learn from historical data. Say you have had incidents where you've written RCAs and you have some new architectural components and you've written some architectural design documents. You can feed all that in as part of the RAG. And then with the next on-call engineer that's able to use that particular agent, all this new information will be used while it's predicting the next steps to do while debugging an issue. With all these enhanced debugging capabilities, we as a team, the Service Mesh team, it will also help us to scale even further. It is able to reduce the toil of the on-call with, like Ryan mentioned, all the less manual debugging that the on-call engineer has to do. And then one of the most important things is to bring down the mean time to resolve, which is an important aspect during incidents. Talking about the future, currently this is just being used by our on-call engineers, but we do have it in plans to also provide it as part of the chatbot that is there that our customers use in our support channel. So many a times we as on-call engineers are called into calls to debug certain issues. So if we can take out the action side of the agent and just provide them with the summary as well as what are the probable root causes as a first pass to whatever question that they have, that in turn would also reduce further toil on the on-call. And right now, all these actions, the kubectl commands and everything are being run as part of a dry run mode and just as suggestions for the on-call and not exactly executing it. Once we gain more confidence, we would like them to even get executed by these agents so as to provide an end-to-end solution. So yes, we do have a booth outside, an Intuit booth. So for whoever is interested in all the different cool projects that the company is working on, please visit the booth. We or our colleagues will be happy to answer any questions that you might have. Thank you. Thanks a lot for visiting, for attending this talk. And if we have time, we are open for questions.
I think we have 3 minutes for questions.
So in your own workflows that you're using, how are you preventing, how are you verifying the behavior of the agents themselves? And what cost is that bringing you in terms of compute costs? Because, as I understand, these agents have their own state.
Yeah, so as per evaluation, this is currently in the, like the initial phase, like I talked about the on-call using them. So for us, from the evaluation perspective, it is right now the on-calls going about what is being suggested by the agent and what they would have done at that point of time to understand how close is it and how much confidence can be, how much can we rely on this agent for now? We do have plans to build up an automation test suite to go over the different workflows that we could have, that this agent could do, and have different success metrics to evaluate how this agent is. Talking from the cost perspective, that is not something that, because it's in the initial phases, that is not something that we have taken much into consideration right now, but that's a valid question which we will eventually have to decide. Mm-hmm.
Yeah, and one more thing about cost, we do take as many steps as we can to reduce the number of tokens and things like that, especially when we're querying logs and metrics. We try and apply as many filters as possible to reduce the amount of stuff that we're pulling down.
How do you think about using one agent with multiple MCP servers versus using separate agents which are specialized in different tasks and having the agents communicate with each other?
Sorry, I think we are running out of time now, so we can take off some questions over there. Sure. Thank you.